Hello everyone, my name is Chunyang Lin from Peking University. I'd like to present our paper titled Adaptive Deep Code Search. This is the outline for my presentation. Code search is a common practice in the process of software development. Developers usually need to search and reuse the previously written code by performing natural language queries over a large-scale codebase. But the accuracy of traditional information retrieval-based methods is not satisfying. Recently, deep learning-based code search methods have achieved state-of-the-art performance because they can better learn the semantic meanings and improve the search accuracy of natural language queries. The basic idea is to train a deep neural model with a large number of text code pairs, then use the model to search on the same code base. For example, DeepX uses two RNNs to jointly embed natural language description and code snippet into the same vector space and use a cosine similarity to compute the matching score. Another example is BVAE. It uses variational autoencoders to encode natural language and code snippet, respectively. However, existing deep code search methods heavily rely on training data and perform badly when applied to a new codebase. For example, if we train a code search model with data collected from GitHub and apply it to a real-world industry software codebase about a smart city. This is an example from the new codebase. We can see that there are some domain-specific words like traffic violation, car licenses, bill that are rarely seen in the training data, so the model cannot represent their embeddings properly, maybe just an unknown token. So existing deep models suffers from the out-of-vocabulary problem on new codebases, resulting in no search accuracy. Well, how to solve this problem? The one solution is to collect enough training data for every new codebase, but it is very costly to annotate text code pairs in regards to both time and money. A second solution is to build domain-adaptive models that can be trained once and easily transferred to other codebases. That sounds feasible, but what to transfer and how? Let's see a motivating example first. Here is a sample from the training data. The text is "create listeners for each button," and the corresponding code snippet contains a for loop for each button B, and action listener. While in the target project, there is the text print traffic violations for each car, and its corresponding code snippet also contains a for loop, but the variable names and master names are different. It is car license list and get traffic violation by licenses. So the observation is that the matching patterns between a natural language text and a code snippet usually exist at different levels of granularity. The lexical level similarities are quite diverse and domain-specific. In the training data, it is listeners and button, but in the target project, it is traffic violations and car. While the syntax level patterns are more general and abstract, these two samples share a similar syntax pattern. If the text is XY for each Z, then the code snippet will contain a for loop for Z, XY. So our main idea is to decompose the semantic matching similarity into two aspects and learn it separately. The first part is domain-specific word embedding, that is a similarity between words which can be hardly transferred to different code bases. The second part is syntactic pattern. That is a sequential matching pattern between the code and the text. And most syntactic patterns are universal across code bases. Well, how to represent the syntactic patterns? We can use the interaction structure of each text-code pair. In Figure A, it is a lexical match matrix between the text correlate listener for each button and its corresponding code snippet. Each cell in the matrix stands for the similarity value between two words. For example, the word create and the word add has a high similarity value. This value can be calculated by the word embeddings that are learned from Codebases in an unsupervised way. Well, Figure B is the interaction matrix between the text print traffic violation for each car and its code snippet. We can see that these two matrices share a similar pattern, and this pattern can be learned by deep neural models in a supervised way. So in this paper, we propose AdaCS, an adaptive deep code search method, which can be trained with data from one code base and transferred to other code bases easily. For the offline training part, it learns domain-specific words unsupervisedly for each code base, and learns the general syntactic patterns supervisedly from text code pairs. For the online serving, it uses a trained model to search and return the ranked code snippet as a result. The model architecture can be roughly divided into 3 steps. In step 1, it learns domain words embeddings by fast text, and in step 2, it constructs the lexical matching matrix for each text code pair. We also add the IDF value of the word into the matrix. In step 3, it learns syntactic patterns using deep neural networks. When it comes to a new code base, we can reuse the trained model, but only substitute the domain-specific word embeddings by unsupervised learning, so it overcomes the out-of-vocabulary problem. The online serving process is the same for different code bases. AdaCS combines the strengths of AI-based and deep learning-based methods. It is both adaptive and accurate. In evaluation, we investigate 4 research questions. RQ1, does AdaCS outperform the state-of-the-art deep code search methods? RQ2 is, does AdaCS outperform the AI-based code search methods? And RQ3 is, how does each model in AdaCS affect its effectiveness? And RQ4 is, how efficient is AdaCS? The training dataset contains Java code text pairs extracted from GitHub, which is also used by previous work. And the test set is a separate code base composed by 3 individual projects, that is Apache Lucene, POI, and GFreeChart, and consists of over 1,600 natural language queries. To simulate the adaptive code search scenario, we filter out all code snippets related to the test project in the training set. We use 2 metrics to measure the performance. Hit at K indicates whether the ground truth is ranked within the top K position, and MRR is the mean reciprocal ranks of the ground truth. We compare AdaCS with 2 groups of baselines. The first group is the state-of-the-art deep learning-based methods, include DeepCS and BVAE that we have introduced before. and the second group is IR-based methods. The Sun is a conventional search engine used by some code search tools, and Skipgram utilizes the word embeddings to compute matching scores, and CodeHow combines the scores of method-name APIs and documents by an extended Berlin model. Here we show the experimental results. For the effectiveness, AdaCS achieved the best hit at k, where k equals 1, 2, 3, 4, and 10, and also the best MR scores, that is 0.62, outperforming existing deep learning-based methods and IR-based methods on adaptive code search tasks. We also compare results for the non-adaptive code search task. As shown in Figure B, AdaCS also achieves competitive results. And we can say that the effectiveness of DIPX and BVE drops dramatically on the adaptive code search task, as shown in Figure A, because they suffered from the out-of-vocabulary problem, but the performance of AdaCS is more robust. As for RQ3, we compare AdaCS against some of its variants. In AdaCS Ind, we use indicator function to calculate word similarity instead of word embeddings. And in AdaCS NoIDF, we remove the IDF values in the matching matrix. We can see that the removal of these modules will hurt the effectiveness. So the word embedding-based similarities and the IDF values are all helpful to improve the performance of AdaCS. In RQ4, we investigate the time efficiency of AdaCS. For the offline training, it takes about 30 minutes per epoch and around 5 hours to reach the local optimal. For the online prediction, it takes about 1.3 milliseconds for each text code pair and about 1.3 seconds for 1,000 candidate code snippets. We can reduce the number of candidates by simple filtering using a vector space model. The time efficiency can basically meet the needs for real-time code search. In conclusion, AdaCS is an adaptive deep code search method which can be trained once and transferred to new code bases easily. It decomposes the learning process into embedding domain-specific words and matching general syntactic patterns. It is more robust and outperforms the state-of-the-art deep code search method on adaptive code search tasks. In the future, we will use parallel deep encoders, such as transformer, to improve the time efficiency, and apply AdaCS to more programming languages and wider test sets. That's all. Thanks for your listening.